Hey everyone, and welcome back to the AI Research Roundup. I'm your host Alex, and today is May 5th, 2025. Alright, today we're diving into this ICLR conference paper, Cellular Automata Accelerated in JAX, published just about 3.5 months ago. This paper introduces a new library, CAX, built on JAX, to massively accelerate cellular automata research, handling everything from classic models to newer neural cellular automata using hardware like GPUs. Alright, so this first figure gives a nice visual overview of the cellular automata types CAX supports. We see examples ranging from classic discrete models, like elementary CAs and Conway's Game of Life, to continuous CAs generating those smooth, colorful patterns, and even modern neural cellular automata, which can learn to generate complex images like emojis or digits. It really drives home the library's versatility. Building on that versatility, this next figure illustrates the high-level architecture of CAX itself. Okay, it shows how the system processes a state at step n. First, there's a perceive module that looks at a cell's local neighborhood using a kernel. Then, an update module takes this perception, applies a function, and computes the cell's new state for step n+1. This modular design is key to supporting all those different CA types. Okay, so that modular design really pays off in performance. These bar charts show benchmarks comparing CAX to other libraries. On the left, for classic CAs like Game of Life, CAX is orders of magnitude faster than CellPilot, up to 2,000 times faster. And on the right, for neural CA training, it shows a solid 1.5x speedup over TensorFlow on that self-classifying MNIST task. Well, really impressive acceleration across the board. Following those impressive speedups, this table gives a more detailed overview of the specific CA models implemented within CAX. Okay, it lists everything from 1D elementary CAs and 2D Game of Life to continuous linear and a whole range of neural CAs, including novel ones explored later in the paper. It really underscores the library's wide applicability across discrete, continuous, and neural types in various dimensions, reinforcing that versatility we saw earlier. Okay, and to really showcase CAX's flexibility for novel research, this figure presents space-time diagrams from a 1D neural CA experiment. So these visuals show the NCA tackling various tasks from the 1D-ARC challenge, like moving or copying patterns. Remarkably, this NCA implemented in CAX achieved higher accuracy than GPT-4 on this specific benchmark, really demonstrating the library's potential for exploring complex, emergent problem solving. Building directly on that 1D NCA experiment, this table breaks down the accuracy comparison with GPT-4 task by task on the 1D-ARC test set. Okay, you can see the specific percentage scores for tasks like move, fill, pattern copy, and others. Notice how the NCA, implemented using CAX, achieves perfect scores on several tasks, especially involving movement and copying, leading to that higher overall total accuracy of 60.12% versus GPT-4's 41.56%. So, that impressive performance against GPT-4 on a specific benchmark really highlights the potential here. Okay, wrapping up, the key takeaways are the massive performance gains CAX offers, sometimes thousands of times faster, and its incredible flexibility for both classic and cutting-edge neural CA research. Well, it really lowers the barrier for exploring emergence in complex systems using these fascinating models. That's all for this AI Research Roundup. Thanks for tuning in.